Assalamualaikum, my name is Shumas. You are watching my YouTube channel. In this video, we will see that how we can simulate methanol production in Aspen HYSYS. So let's start. First of all, we will see that what case study we are having. So we are having a case study in which we are having a feed flow rate. Its flow rate has been given to us. This temperature and pressure is also specified. So now what we have to do, we have to convert this feed flow rate feed flow rate reactants into methanol and water via this reaction, and this reaction is happening in a continuous stir tank reactor CSTR. So now the temperature and pressure of a CSTR, the operating temperature and pressure of CSTR is also given, but is different from the feed temperature and pressure. So we will use a compressor and a heater to make our or to fulfill these temperature and pressure conditions. So after the reaction will happen in the CSTR, we will be having there will be not 100% conversion, so we will be having unreacted reactants and our products. So unreacted reactants and products will be separated in a separating drum. Its pressure has been given 20 bar. The best temperature will be at which above 95% of separation of methanol and water is achieved. So now in our separator, we will separate out our unreacted CO2 and hydrogen, and this methanol and water will be in liquid form and will separate out. For separating out methanol and water, we will use a distillation column. Its operating pressure and reflux ratio has been given to us. So from this distillation column, we will separate out methanol and water. We will perform our calculations in shortcut distillation method, and then from shortcut distillation method we will also perform the calculation to find 99% of purity of methanol in RadFrac column as well. So now I had made a small schematic diagram. So this is the diagram that we will be following or we will be simulating in our Aspen HYSYS. So we will be having a feed, a compressor and heater to make the inlet conditions up to the CSTR inlet condition, that is temperature is 280 and pressure is 80 bar. So this valve is reduced, will be used to decrease the pressure to 20 bar, and this cooler sorry where it is so this and this cooler will be used to find the best temperature for separation in our separating drum. The unreacted our unreacted reactants will be recycled back, and our bottom that is comprising of methanol and water, again we have used a valve to decrease the pressure, that is 1 till 1.3 bar at which distillation will happen. And after this, we have used a distillation column for the separation of methanol and water. So without further delay, we will directly move to our simulation. After moving to the simulation environment, I am going to add my components. So my first component is hydrogen. My second component is CO2. So I am adding CO2. And my third component is methanol. So I am writing, so it is not my, it is also a component and my product. So methanol. After that, the last component, and that is also my product, is water. So I am writing adding water. So now you can see that all my components have been added. In the fluid package, I have already selected, so I have selected Penn Robinson for the simulation. After that, we will go to the reactions. In reactions, now I will specify the reaction that is being performed in our CSTR. So the reaction that is happening in our CSTR, we have to define over here in Aspen HYSYS. So I will press this add. Here I will press this add button. So now this reaction is simple rate. So the reaction I am going to specify is simple rate reaction. So I will press this add. I will press this double press on this reaction. So now here I will add my reaction. So first of all, my reactant is carbon dioxide, and it is reacting with hydrogen to produce methanol and water. So now I have to specify the stoichiometric coefficient. For reactants, we have to write -1 or minus sign, and that will show that we are specifying the reactants. I am specifying for products, you have to go with positive integers that will specify that you are specifying your products. So now you can see that balance error is zero. My equation is balanced. Here, these are good to go. You can go with molar concentration. Our reaction is happening in our liquid phase. No, it is a vapor phase reaction. So you will specify here as vapor phase. And now I will specify my forward reaction A, and this is the it is a constant A, and this is the activation energy. So for A, I will go to my case study. So it is the value of A is 14,000. So I will copy and paste it here as 14,000, my value. After that, the activation energy is 15,000 kilojoule per hour. So I will write as 15,000 kilojoule per hour. So in the kinetic rate to have, you have to specify the minimum, the first this constant A when you are specifying a simple rate reaction. So the value is 1400. So I will write as 1400. If I press OK, so you can see that it is saying that it is still not ready. But now, after pressing click, it says that all the minimum requirements for specifying a simple rate reaction has been completed. So I will just close it, and then you have to add this reaction to fluid package. So press this and add this set to fluid package. After that, I have specified my reaction, and now I will go to my simulation environment. So now we are present in our simulation mode. In our simulation mode, I will again go to my small flow sheet. So first of all, I will go to my flow sheet, and from model and streams, I will drag a compressor over here. And in compressor, I will define my feed stream. So I will double click on it. Inlet is my feed, and for outlet, I can write as compressed outlet, compressed feed, you can write it as. In compressor, you have to define an energy stream, so I will define an energy stream. In parameters, it is all good to go. And add in the feed stream. Now I will define a feed stream. So inlet temperature was 100 degree, its pressure was 20 bar, so 20, and from here I will write as select 20 bar. Now what was the feed flow rate? So feed flow rate was 1500 kg mole per hour. I will double click on it, and for hydrogen it was 0.70, and of carbon dioxide was 0.30. I will press this OK, and now you can see that I will press OK, and now you can see that after pressing OK, my all feed stream unknown values have been defined. But now in the compre but for compressor simulation, I have to define the outlet pressure. So the outlet pressure is 80 bar. So I will define as 80 bar. Where is bar? So my outlet pressure is 80 bar. So now you can see that my calculations have been solved. Now you can see that the outlet temperature after the heat of compression has been changed to 344, but our inlet temperature in the reactor was 280 degree. So now we will use a cooler here. So I will select a cooler, and I will double click on it, and then I will press my inlet stream as compressed feed. Again, for the cooler, you have to define as G stream. I can write as E1, and out you can say as feed to reactor. So now it says that unknown delta P. So now I will go to the worksheet, and here you will write the delta P. So I am giving 0 delta P, and I can write as 800 800 kilopascal as my outlet feed pressure. So now, as it is a cooler, so you have to define the outlet temperature. So our outlet temperature will be 280 degree. That was our reactor inlet temperature. That was defined in our case study. So now a little cosmetic changes. After that, I will select a reactor. So you can rename. So you can rename it as compressor here from here, and you can also rename it as cooler or heater, whatever you want. After that, I will apply, as now you can see that my stream is now at the condition of reactor. Reactor inlet conditions, temperature is 280 degrees, pressure is 80 bar or 8000 kilopascal. So now I will again go to my model and model palette. From here I will select reactor, and this is a CSTR. So I will select the CSTR, place it over here. I will double click on it, and I will drag it to the top. In streams, the stream is feed to reactor. So now, as we are having only vapor reaction in vapor phase, so you can write as reactor out, and in liquids you will not be having anything. You can write as L, as it is a isothermal react, and the reaction is isothermal. So we have it is not an adiabatic reaction, it is isothermal reactor. The outlet temperature and the inlet temperature conditions are same, so you have to define the energy stream. If you are working with adiabatic reactor, you do not need to define this thing. If you are working on an isothermal reactor, then you have to define this energy stream. So as we are as we are simulating CSTR in isothermal mode, so I will give my energy stream. So it is E2, so it says requires a reaction set. I will go to the reactions, and we are having only one reaction set. So now I had attached my reaction set, and it says now volume not specified. So now what was the volume? Our volume was 7.5 meter cube. So here we will come, and I will write as 7.5 meter cube as my volume. So now it says that unknown duty. It is saying unknown duty because as it is an isothermal reactor, so you have to define the outlet temperature as well. I will define my reactor out temperature as 280 degrees. So after defining my temperature, you can see that my simulation has been solved. I will double click on it to see my reactor out composition. So you can see that only hydrogen is coming over here. No CO2 and methanol is present. So I think we have made something wrong. So let me see that where I have done something wrong, because no carbon dioxide, that is the component, is present. So let me see if I double click on it. So see that here it is only hydrogen has have been selected. So the original composition was 0.70% was hydrogen, and remaining 0.30% was carbon dioxide. So I will change it, and now I will again go to my CSTR, and here you will see that now you can see that methanol and water, the reaction is completed, reaction is happening, and methanol and water is being produced in our CSTR. So now you can see that only 18 moles of hydrogen is being going out unreacted. Out of how many moles? So I will go here, and out of mole flows. So out of 1050 moles, only 18 moles of hydrogen are going out as unreacted. So that's CSTR has been simulated. After that, our next task is to use a separating drum at best temperature we have to find, and at 20 bar pressure. So we will reduce the pressure for flashing to happen. So I will go here, and here I will select a valve, or you can see that in pressure changer it is a valve, so I will apply a valve over here. And after valve I will go to my separators, and here you will use a simple separating drum over here. After this I will click, I will just a few cosmetic changes. And now I will double click on it, and it is reactor out, and my outer outlet will be I define as separator inlet. Separator separator inlet spelling, I have written wrong spelling. Separator inlet. After that it says that unknown delta p, go to the worksheet, and here you have to write 20 bar as your outlet pressure. 20 bar, where is bar? So it is bar, 20 bar. So you can see pressure has been dropped. After that you will just double click on this separator, and this separator is inlet is separator inlet. The outlet vapors will be the unreacted hydrogen and carbon dioxide. So you can write as gases, and for the liquid it is the liquid, you can write as liquid, and it is consisting of methanol and water. So no need to give energy stream. Go to the worksheet, and all thing is okay, so it is okay. So now you can see that uh, no separation is happening. So all of the gas is entering, all of the gas is leaving, because we didn't we have only reduced the pressure, but we did not install the cooler. If we originally go to our flow sheet, so we have to install a cooler over here. So now for the cooler, I will click on this stream, and you will press this brake connection. So now when this tick will happen, tick will come. So now brake connection is removed. So I will again go to my model stream, and here I will use a cooler. So cooler over here. So I will double click on it. Its inlet is uh, sep separator inlet. So you can write as energy stream E3, and for you can write here as separator inlet 2. So now if I drag it a little top, it says unknown delta P. So you can specify the delta P over here also, but I find it convenient to write my delta P or outlet pressure over here. So no delta P, so I will zero delta P. So now it says that unknown UT, so it means that you have to define the outlet. You have to define the outlet temperature. So I can write here as I have a high, so it is a hit and trial method for finding the best temperature. So in Aspen Plus you can use the design spec for getting the optimal temperature, but in Aspen HYSYS you will have to do some hit and trial method. So 40 or 35 degree is the best temperature, so I will just write 40 degree for my separation for the outlet of this cool stream. Outlet temperature of this and outlet temperature of this so I had defined 40 degree temperature for this steam that has been pressure has been reduced, and now it is cooled and ready for flushing to happen. So now I will double click on it, and again go to the design. In streams I will select the separator inlet 2, and you can see that my simulation has been solved. Go to the worksheet, and here you can see that separation is happening. So liquid and with gases have been separated out. So if you double click on it and see the mole flows, so you can see a large amount of originally the all or almost all the methanol and water is present in our bottom stream. gases, in gases, if you double click on it and see the mole flows, so you can see that a minimal amount of methanol and water is going into the gases. Almost all the you can say that all the carbon dioxide is going into our gas stream. But if I double click on it and go to the mole flows, so you can see till now 26 kg mole of carbon dioxide is still going into our liquid. That is not feasible. You can decrease the temperature. You can decrease the temperature to more less temperature. So let's say I write as 30 degree, and now if I go to again here and see that mole flows, mole flows. So now you can see that carbon dioxide value have been increased. So let me increase the temperature. Sorry. So again, if I go to here and give the temperature 45 degree, so now see, we'll see that. So now mole flows. So now the carbon dioxide value is being reduced from 26 degree to 26 kilomoles to 24. So now you have this is an hit and trial method. You can optimize your carbon dioxide that is going with the liquid. So now I will now we have to recycle these gases into our feed stream. So now for recycling, I want to change the direction of arrow. So I will just press this rotate, and you can see that the arrow has been direction has been changed. So now for recycling a stream in Aspen HYSYS, you have to use this recycle module here. In Aspen Plus, you can just recycle it, but in Aspen HYSYS, you have to use this recycle module for recycling a stream. So now I will press this recycle. Its inlet is gases. So here I can write as recycle. Its outlet stream is recycle. So now I have to apply a mixer over here. So I will press this again. I have to break connection, so I will press this break connection, and as soon as a tick happens, so now the break connection is break. I will again go to this model, and here I will press a mixer over here and double click on it. So inlets are my feed. So it is, so this is feed, and the other will be our recycle. So it is recycle, and outlet you can write as feed to. It's feed to. So now just uh, double click again on the compressor and give its inlet feed to this feed to. So now feed to, and you can see that simulation has been solved. So if I go to my results, so here these are the results. I will double click on it, and if I go to the mole flows, so you can see initially it was 343 and 343 kmol of methanol is being produced, but now it has increased to 348 kilomoles of methanol. So with recycling, our methanol production has been increased. So after that, now in liquid we are having methanol and water. So here you can see that we have to again apply a valve, and we have here in the case study vapor, and so it is wrongly written as hydrogen and carbon dioxide. We were only having CO2 and hydrogen, no carbon monoxide is present. So now distillation, we have to perform distillation for the separation of our methanol and water. At the pressure is 1.3 bar, and the reflux ratio is 1.6. So I have at now I will again use a valve for decreasing the pressure. So here is a valve. After that, this is valve. I will double click on it. Its inlet is liquid, and you can write as liquid 2. So now unknown, it says as unknown delta P. Go to the worksheet, and here you have to define the outlet pressure. So it is 1.3 bar. So 1.3 bar. So now it says OK. After that, I have to, in the question it is saying that you have to use, firstly you will perform calculations with shortcut method, and then regress to, with regress to. So I will go to the separators. Here, this is the oh sorry, this is shortcut distillation method. So I will drag this shortcut distillation method to over here. I will double click on it. Here you can write as inlet 2. For condenser duty, you can give as E4. For reboiler duty, you can specify energy as E5. In distillate, you can write as methanol, and bottom you can write as water. After that, go to the parameters, and here you will have to define the condenser pressure, as the operating pressure is 1.3. So condenser you can write as 1.2 bar, 1.2 bar, and for reboiler you can write as 1.4 bar, a little higher than the operating pressure. So now the flux ratio is 1.6, that was defined to us, and now it says that light key in bottom. So what was the light key in bottom? We want to have only water. So the light key is methanol, and so light key in bottom we want 0.99% of separation. So the light key we want the light key will be methanol, and heavy key in distillate. So the heavy key in distillate methanol, we want methanol is light key. So the in distillate the heavy key will be water. It is water, and also here we want 0.99% of methanol in the top product, but it is the light key, so we want water to be in the top product, zero, again 0.01%. So now you can see that the simulation has been solved. You can go to the worksheet and performance, and this thing you can take a snap of, because these things will be used for the rigorous distillation method. So now if we just see that what was the minimum number of trays, the actual number of trays is 12. The optimal feed stage is 6 stage. So that are the values: condenser duty, heat duty, reboiler duty, the vapors load, all the things, stripping vapor load, all the things have been defined over here. So now go to the worksheet, and in the worksheet, I will double click on this methanol and mole flows. So you can see that the mole flows. So these are the mole flows. So a large amount of methanol is present over here. Mass flows. If we go to the mole fraction, 0.01% of methanol is present, and rest carbon dioxide is also accompanying with this. So now if you increase the purity of this methanol, so what you have to do, you have to remove this carbon dioxide from this stream, because the let me say that if I will double click on it, and in the design parameters, I reduce the this to 0.001%, and let me see that some changes happen or not. 0.001%. So now I again go to the worksheet, and here I will press this So now you can see that its purity of methanol has been increased, but if carbon dioxide is present, so you cannot increase the purity above 0.95%. So we will say that 0.90 is acceptable for us. Otherwise, if you want to increase the purity, you can just uh, you can just you can just add a component splitter over here and remove the carbon dioxide. And if you remove the carbon dioxide out of the stream that is consisting of only methanol and water, you can achieve the 0.99% or above 0.9% of purity of methanol in the top product. So now this is the shortcut distillation method. So now if I so now uh, I will go to my performance. Uh, I will go to SnapTube, snapping tool, sorry, and I can just take a snap of this, as these things can be used in our rigorous distillation method. So I will click on it and I will delete my shortcut distillation method. After that, I will go to my distillation column. This is my rigorous distillation column method. This is my rigorous distillation column model. So I will double click on it, and here I will just specify my inlet stream, that is liquid 2. So for condenser, I have given for condenser duty, it is I can write as E4. For reboiler heat duty stream, I can write as E5. Or the last ones for condenser, we are using total condenser, and you can write as methanol. And for bottom product, you can specify as bottom. So now the number of stages that were calculated in the shortcut distillation method was 11. So I will write as 11. So after that, I will all the things have been specified. So I will press this next button. So it's once through regular HYSYS boiler, and good to go. So now I have to specify my condenser pressure. So condenser pressure I will again write as 0.2 bar over here, and reboiler I can write as 1.3. Oh, sorry, 1.4. 1.4 bar. After that, I will press this next, and here the optimal condenser, and these are optional things. So I will press this next button. So now here is the liquid rate and reflux ratio. So I know the reflux ratio, so I will write as 1.6. So I don't know my liquid rate, so I just press this done for now. And now you can see this window has been opened. So you just go to this monitor, and here you can see that you need to specify any two things. Here you can see that degree of freedom is 0 because it is ticked over here. So if I uncheck it, so it is 1 degree of freedom. So I have specified my reflux ratio. If I have to specify any other thing. So if I want to specify my methanol purity in our top product. So from here I can write as add spec. From add spec I can uh, comp column component fraction. So I will add the spec. It is a column component fraction. So now just it is a stream. So I will select this as a stream. Stream is methanol, and its mole fraction spec value I want to give as 0.90. 0.90 of methanol in the top product. So components, I am of which component of methanol. So now you can see that all things have been solved, or the input is complete. So now degree of freedom is 0. So I can press this run button, and you can see that the simulation has been converged. So I will go to my worksheet, and here you can see that methanol. If I double click on that, and so now you can see that 0.90% of methanol is present in our top product. So now the purity has been achieved. As in the case study, it was said that you have to gain. So here you can see that it is saying that 0.99% of purity is to be achieved. But as I had already told you that here carbon dioxide is present. Till then, this carbon dioxide is present here, the purity will not be achieved. For getting here 0.99% of mole fraction, so let me remove this carbon dioxide from this stream. So for this simulation, I will cross it, and here we will have to add a separator. So I can disconnect the stream, break connection, and now it is over here. Go to your model palette, model palette, and here from here you can select a component separator. So this is a component separator. Drag it over here, and in this component separator we will separate out our carbon dioxide, and the stream that is free from carbon dioxide will be fed to this distillation column, and then we will get methanol purity to 0.99% of methanol purity in our top product. So I will double click on it, and here I can write liquid 2, and in the parameters delta p is empty, so here I can write what is the delta p. So the operating pressure for our distillation column was 1.3 bar, so I will write as 1.3 bar. So now after that I will double click on it. So the inlet stream will be our liquid 2, and the overhead stream, you can write the overhead stream as the carbon dioxide purge. So CO2, you can write as CO2 in the top product. For the bottom, you can name any, you can write as distillation field. So good to go. After that, it says that we are having unknown splits. So we will go to the parameter. Here you will specify the vapor fraction of our CO2. So it is a gas, so it will be left here as a gas. So I will write as CO2. After that, it says that unknown splits. Go to the unknown splits. After that, it says that unknown splits. So I will go to the unknown splits here, and these two, CO2 and distillation feed, is showing our streams. So I want my all CO2 to be in my CO2 stream. So I will double press here as 1, and and in hydrogen I can also say that if some hydrogen is present, it can also go to the CO2 stream. So here and now methanol and water I will write here as 1. So now it says that unknown overhead pressure. So I will go to this. So here you can write your operating pressure, that was 130 kilopascal. So it says that unknown bottom pressure, you can also write here as 1.130 kilopascal, or it is equivalent to 130 bar. So now it says that your pressure, your simulation has been converged. So after that, double click on it. So now this is your stream that is free of carbon dioxide and small traces of hydrogen that were present in our this stream that was being distilled to separate methanol and water. So I will delete this stream. So now after that I will just double click on it and give my inlet stream of this distillation column to distillation feed. And now I will go to my monitor, and here I will press this run button. So now you can see that my simulation is converged, but I have to now give my more purity to 0.99%. So I will give it to 0.99%. So that is 0.99% is the methanol purity in our top product, because now we can achieve it because we have removed CO2 from our feed stream. So I will again press this run button, and now you can see that my results are available, and the simulation is converged. I will go to the worksheet and double click on it, and here you can see 0.99% of methanol purity is achieved in our methanol stream, that is top product. You can also find the mole flows, that is the, sorry, this is the mass flow and this is the mole flow. And for in water, you can double click on it, and here in methanol water purity, you are getting 0.9557% of water here. So now we will see that what final flow sheet that we are having. So it is our final flow sheet. So I hope you like the video. Inshallah, meet you in another video. Assalamu alaikum.